Hello, namaste, and a very warm welcome to all the viewers of India Rising. I'm Anjali Swami from Bharat TV. Dear viewers, we are literally over the moon. Sorry, at the success of India's Chandrayaan 3 lunar lander and rover mission. Today, I have with me four happy people to discuss this. Two are our usual participants, Dr. Nivedita Haran, you all know, retired senior IAS officer, Dr. Narayanan Komarath, retired professor of aerospace engineering, and presently chair of the Taksha Institute's Alliance for a Space Economy, that is a whole economy based beyond Earth. We have three expert guests in addition today. Shashank Devangare, he was with us a couple of episodes ago. He's from the financial products industry, and we'll talk about the medium and small industry opportunities arising from India's space program. He's also a space enthusiast thrilled at Chandrayaan. Arun S. Vishwakarma is a San Francisco Bay Area entrepreneur, expert on electronic systems, software, and studies aviation, space, and rocketry. We can ask him how a robo lands so precisely on the moon. And we have a very special guest today, Professor Satyanarayan Chakravarti. He is a professor of aerospace engineering at Indian Institute of Technology, Chennai. So, India's top technical institution is where he comes from, and he works with some 18 startup companies, including Agnikul, which has developed a 3D printed rocket engine. He has been with the Indian space program since the 1980s, literally among the best of rocket scientists and rocket engineers. So let me get them on the stage. Nivedita Haran, Narayanan Komrath, Shashank Bhavangare, Arun, and Professor Satya. I'm really delighted and over the moon that all of you are here today as my panel guests. So let's begin. Narayananji, can you launch the proceedings?
Namaste. I remember seeing those colored clouds as a child. Those were released by the Rohini sounding rockets. I didn't know that name at that time, from Tumba in Kerala in the 1960s. In the 1970s, they told me at the IIT that India is a poor country. We have to go with solid rocket propellants, not these exotic cryogenic engines needed for moon rockets, etc. So one would have to go to America to learn about hydrogen engines. But India took an immense risk with those solid rockets. India was the first nation to reach orbit with a four-stage all-solid rocket system, and did it right the first or second attempt. I'm not totally sure. I have actually a model here that I think Professor Satya gave me a long time back. Professor Satya, can you please take us through this transition from the early days of sounding rockets and solid propelled rockets to today's propulsion systems? Rocket science in 5 minutes.
That's very fascinating. That's very fascinating journey for ISRO. So I think there were essentially three steps that they took to PSLV, in my view, if I can think about it. I think the first step is in the 1963 when ISRO was not even called ISRO. It was called INCOSPAR. It was an Indian Committee for Space Research or something like that. And those were the days when Vikram Sarabhai was at the helm. He was actually more of a physicist, and he was interested in atmospheric physics. So he had to do rockets, not a ton, study atmospheric physics. That's where the sounding rockets came up. So the sounding rockets were the Apache sounding rockets, which were inherited from the US. About 6 people were sent to the US exclusively to work with NASA to understand this. And they got actually the solid rocket technology rather than. So I don't know what exactly was the reason for that, because by that time the world had actually, as Professor Narayan said, the world had actually moved towards liquid rockets, cryogenics, all of those things. But solids were kind of coming up. The space shuttle was actually going to use the largest solid rockets in a decade later. So I think India jumped on solid rockets. So fast forward to 70s, Vikram Sarabhai unfortunately passed away in very mysterious circumstances, and Satish Dhawan took over, and that was a very important transition. I'm not going to name names beyond this because these two people were actually the pillars of what ISRO is today. And Satish Dhawan actually put in place a system because he's actually a fantastic scientist himself from Caltech and IISc, and an amazing personality. He actually insisted that he would continue to be the director of IISc while also taking up the chairmanship of ISRO, like two huge positions at the same time. And that's also the reason why ISRO is headquartered in Bangalore. He insisted that that needs to be there, right? So these were the terms with Prime Minister Indira Gandhi that he had, and then they actually got into the SLV program that Narayanji just mentioned, and it turned out that uh, Dr. Abdul Kalam was actually the project director of this. They failed the first time, so there is this very illustrious uh, anecdote that Dr. Kalam has mentioned in his biography of what is leadership. So the first time when they failed, Satish Dhawan took the complete blame for it himself. And the second time when they succeeded, he center staged Kalam to the front saying, this is the team that actually won. And this is a mark of leadership that's now being talked about in all the business schools in India. And they succeeded. But then they also had crafted this ASLV. So we were going to school at the time, and we used to joke that SLV was a sea landing vehicle, and the ASLV was another sea landing vehicle, and so on, because all of these would actually land in failures into the Bay of Bengal. But it's only when I got into college and started learning what it was all about, and then I spent the summer of 1990 completely spending my time in uh, let's the what is now the Satish Dhawan Space Center, but was generally called SHAR, Sriharikota Range. Um, so that's when they were transitioning from ASLV to the PSLV. So uh, with the later day analogy of the Jurassic Park, what was actually looking like the just the Raptors, which is the ASLV and the SLV, all the stuff, the making the engines, making the rocket motors, making the launch pad, everything. They were constructing the PSLV stuff, and that looked like the T-Rex, right? So this was so huge when compared to what was happening. And now I understood why all those ASLV failures were so important, because they were well crafted failures from which you would learn what not to do with the PSLV, because the PSLV was so huge you couldn't afford to fail. And that's exactly the reason why we are actually continuing to do the 56th successful consecutive successful launch over the last 20 or 30 odd years now, 20 plus, a little less than 30 years, right? Continuously PSLV is actually become the workhorse from the mid 90s onwards. And then actually they got into the GSLV Mark II and then the GSLV Mark III, and that's where they are as far as the launch vehicle is concerned. They then got into the cryogenic engine program in the 90s. They had setbacks in terms of technology transfer from Russia with the US intervention. So we got the engines. Some of them did not work very well. So these things happen, and then we perfected our own cryogenic engine for the Mark II, and then now a new engine for the Mark III, and so on. Yeah, so all of these things have happened through about 2015. I think from 2016 onwards, we have been working with the Mark III and the PSLV. Occasionally, we also actually use the Mark II. So it's actually a family of about three vehicles that India operates on its launch vehicle arsenal.
Satyaji, from what I remember, the earlier conversations that I had with you, that it took almost a decade for you to build that launch pad. Is that right?
Yes, absolutely. I was fortunate to actually get that opportunity to work, alongside my ISRO scientists, colleagues, in actually building the second launch pad that is suitable for launching the GSLV Mark III, which is the largest heavy lifting vehicle that ISRO has built. To give you a context, the first stage of the PSLV carries 139 tons of propellant, solid propellant. The GSLV Mark III actually has 205 tons of propellant in each of two boosters. That means we are actually talking about suddenly going to 410 tons of solid propellants that is going to spew, each of them actually spewing through its nozzle something like about a 2 ton per second amount of gas. So that's a kind of mass flow rates you will actually get, like about 4,000 kilograms of gas that's coming out of this. And ISRO was actually now beginning to worry, hey, if this much exhaust comes out at the launch pad, will it not give rise to a lot of launch acoustics, which is essentially aerodynamic noise, if you will. And that could be of such an unbearable magnitude that it can go and screw up all the launch vehicle electronics, the payload electronics, and so on, because electronics have only a certain threshold of acoustics that they can bear. So we had to actually do something to, kill this acoustics. See if we can actually suppress this noise. And we spent a lot of time working on subscale launch pads, which are like kind of like toy launch pads made out of cement, that can actually even hold in your hand. So it's like a 100 scale, a 120th scale launch pads, and so on. And then finally went to about a 112th scale, which was now beginning to become much larger. And so we actually trained different locations of water injection, optimized the pressure, optimized the flow rates, and so on. And finally did the whole thing at about I think we spent about 40 crores, is what I understand. But the original estimate 10 years before that work was actually 240 crores. So we saved like about 200 crores in just doing R&D. And we have the most efficient noise suppression system that was laid out on the launch pad there for this purpose. And it's still improving further and further.
That's very impressive, Dr. Satya. Also,
And that's what just took the Chandrayaan 3 in a couple of months ago.
right. Just for the benefit of our viewers, I want to let everybody know that Dr. Satya was right there in that activity room where the launch and the actual landing was happening. He is one of those ISRO scientists who are right there. I should have said this right in the beginning, but um,
Oh,
I,
no.
I thought this is the appropriate time to let everybody know. So over to you, Narayanji. I know you have a lot of questions, so please go ahead.
I'll be shorter much time from next time.
Oh, okay. Yeah, my next question was really to Arun about that final 40 minutes or so of nail biting tension. Of course, I was on TV the first time also, and certainly this time. How do you get a robot to slow down from 1700 meters a second down to hover over the lunar surface, almost like a helicopter, and then touch down precisely, and then roll out a rover? How do you do this?
That's a very interesting question, and for that, we need to understand some of the basic aspects of this landing. And the difference between Earth and Moon is Moon radius is 1700 kilometers, whereas Earth radius is about 6,400 kilometers. So roughly more than 3.5 times smaller is Moon radius. And obviously the gravity is 1/6 of Earth. And so in this particular mission, our targeted landing zone was a big landing zone compared to Chandrayaan 2. Chandrayaan 2, the landing target was 400 meters by 400 meters. And in the case of Chandrayaan 3, it is 4,000 meters by 2,500 meters. So more than 60 times bigger. But still, if you have a landing zone that is that size, um, given that the line of sight at 30-kilometer altitude, that's when the deorbiting maneuver will start, the line of sight is 500 kilometers. And so if I may request Anjali ji, if you can put that diagram of the Chandrayaan 3 trajectory, might be useful for the viewers.
Um, yeah, I can actually try that. I'm having a little bit of technical difficulty, but we'll just get to that, Arunji. Uh,
Sure.
Meanwhile, I have a question for Nivedita. Nivedita, could you please tell us how did India's government keep ISRO going through very difficult times to get to the stage?
Thanks, Anjali. Thank you. Yes, as you rightly said, we all are over the moon, and you should have seen the kind of excitement that was there in India everywhere, and I think that really makes us proud. Uh, I'm not that well suited to talk about the budget on the Science and Technology Ministry and so on. But overall, what I can say is that in a country like ours, uh, when you have so many pulls and pushes, so many requirements, the development side, agriculture side, the infrastructure side, uh, it does happen. It does make a difference uh, how the prioritization takes. And it is a fact that there was a time when this was probably not the top of the priority. Science and technology probably was not the top of the priority. But I think Chandrayaan 3 has made a kind of impact where now everyone talks about it. And it has been the result of the budget having gone up substantially, the scientists having taken the challenges, and as Professor Satya mentioned so lucidly, uh, it, it's a, it's not just we have done it. We have done it with so much of economy. The that is The world is surprised at it, and second, there is so much of indigenization in it. It's all Indian, and I think that is the proud moment that gives us the proud moment. I, as an administrator, I want to mention that events like these are actually not just important from the scientific point of view. Of course, it's very important. And I spent about 3 hours yesterday with my scientist uncle trying to understand what are the kind of experiments that are happening on the moon. And therefore, that is very important. But looking at it from a a layman's point of view, an incident like this, an event like this, helps to bring the country together. And it has done that. Everyone, wherever you go, people are asking. Even the local, the Kirana store, the man says, what exactly happened, madam? Tell me what happened. So you see, that kind of confidence, it builds our confidence, it builds our self confidence. And most important, which as people, as public servants, and in every sector, which is so important in our country, it coerces us into do better. And you, even people sitting out, people like you, Anjali, it gives you that kind of a push to do something for the country. I think that is the main takeaway that I would like to mention from here.
Absolutely. And Arunji, we will get back to you. Just trying to still work at those at the
I,
technical
I have I have
difficulty.
shared the screen. I have shared my screen with that picture. If
Okay,
that would
let me
help,
see.
Arun. I don't
Okay,
know if
there you go. Yes.
Oh,
So
can you put the other picture, please, for me?
the other one.
Yeah.
Okay, let me stop sharing and do this.
okay, so is that are you going to share another picture, Satyaji?
I'm
Or
just trying. I didn't know that he wanted the other picture. Let me just do that right now. Yes,
Yeah.
there are two
That's an
pictures.
image. It says Chandrayaan 3 trajectory. That one.
Yeah, yeah, I'm just getting there. I'm just getting there. Just getting there.
So, Anjali ji, I'll just repeat my statement so there's continuity
yes, please. Yeah.
later. Okay. Once that picture comes up. Yeah.
Do you see my screen?
Yes.
Yeah.
Yeah. That's great. So, talking about some of the basic aspects of the landing, um, this particular landing would be started at 30-kilometer altitude. And at that point, the line of sight is barely 500 kilometers. And as you could see in this particular diagram, um, the challenge is that we have to start the maneuvering about 750 kilometers from the point of landing. So at that point, the landing point is not even visible because of the curvature of Moon. And so the challenge is, in this 750 kilometers, we have to zero out all the kinetic energy uh, of that particular craft, which is moving at 1,680 meters per second, to zero at precisely 750 kilometers and at an altitude of about 1 kilometer, because that is where we will start the vertical descent. And that is the big challenge. And to do that maneuver, one need to also understand that the lander, which has got the Pragyan inside, its dry weight, that is without the fuel, is about 750 kg. And on Moon surface, it only weighs about 132 kg. And the whole craft has a fuel of about 940 kg, and that fuel is used by up to 4 engines, which are pressure fed, each generating about 81 kilo force, 81 kilogram force. So, so these are the resources available. And once we know that these are the basic constraints, then the landing challenge is really addressed by two major subsystems there. One is precise navigation subsystem, and the other is precise control system. So unless we know where we are, the control system cannot figure out what needs to be corrected and how can we decelerate um, to hit that target. So both these systems were more very robust in this Chandrayaan-3 compared to the previous mission, with a failure-based design, so that there were additional redundancies that were built in um, to make it almost bulletproof. Now, precise navigation is quite difficult on Moon because the initial uncertainty of the Chandrayaan 2-3 orbit is hard to determine, and also because the lunar gravity is uneven. So, given these two considerations, a flight which is based purely on inertial navigation systems uh, is not very attractive or likely to succeed on its own. But on the other hand, ISRO had in hand very high resolution 3D and 2D moon surface mapping data by the survey that was done by the Chandrayaan 2 mission. That was the previous one. And that survey produced imaging with an accuracy of, or the resolution of 25 centimeters per pixel. That is all very great for finding out where to land, but still is not as great to pinpoint plan everything. But with these two assets that we had in hand, what they did was in Chandrayaan, they used a navigation system that is essentially an inertial navigation system with terrain mapping correction. And that comprises of, like any other thing, it's got an inertial measurement unit that our spacecrafts have been carrying all along. It's got laser gyros and accelerometers, and with certain amount of drift capability, etc. But this IMU is supported by other navigation supports, comprising of celestial navigation system, which is the star tracker, that allows you to give the craft's attitude, the orientation in space, and also the rough position in the spatial coordinates. It also had very, very sophisticated this time altimeters and velocimetry, which used Doppler laser navigation, and for the RF1, it used a millimeter wave Doppler navigation as a standby. So they had two standby systems supplementing, supporting the initial navigation system to cancel away the errors. They also had redundant sensor types, more types of sensors, and each type of sensor, they had a lot many more of those units. So that even if the craft is tumbling, for example, the system can precisely measure where it is, at what rate it is tumbling. So all these redundancies really made the necessary framework to make a very, very robust flight system that can accomplish this. And all of these sensors, their outputs were going through a model-based Kalman filter so that they can figure out if the sensor is abnormal, you can eliminate that data set. And all these information were then fused together to form a very, very robust navigation system. So yes, the climax of knowing great success or failure of the whole mission can be very nail-biting. And the biggest tension, in my view, was in the initial 14 minutes. That is when the craft was doing rough braking, as you can see in this diagram. The rough braking really is for a pretty long time and a long distance. Um, and the objective of the rough braking is that you are on an elliptical orbit. Uh, Nominal orbit altitude was 30 kilometers from moon surface. In reality, in this mission, the actual orbit was about 25 kilometers. So from 25 kilometer, the rough braking essentially kills the speed, which is at 1700 meters per second, to bring it down to a very low amount and reach a point which is 700 kilometers out and at an altitude which is about 7 kilometers. So that to me was very, most important. So rough braking was initiated here, as you can see, at a perigee of 30 kilometers. Velocity was 1680 meters per second. And at that moment, the craft had about 900 kilos of fuel. And it fired all the four engines, generating 81 kilo thrust. And at that time, the craft was almost parallel to the moon's surface. So the objective was to reduce the velocity, decelerate the velocity. So during the flight, the velocity was computed by the inertial navigation system. And the inertial navigation system, however, has got absolute and progressive error buildup. As it continues to fly, the position is known with more and more uncertainty. And this is where the positional error is corrected by camera images that are looking below as well as looking forward and back. And using the information that is coming from the camera and comparing it with the earlier high resolution moon mapping survey, it allows the navigation system to compute really where we are on top of the surface and accordingly correct the initial navigation system and whatever error it is projecting down. So in this process, the altitude was very accurately measured by laser Doppler velocimeter, which has got four beams. Much like in the previous generations, we used to have Doppler navigation system. So instead of RF, it uses laser. And so in case of the failure of this laser Doppler velocimeter, there was a backup millimeter wave Doppler navigation system, which is amongst the most accurate system. So these sensors and navigational inputs, they were validated and cleaned up by the Kalman filter. Then all this information was fused together. That resulted in a very, very robust and accurate navigation system that then feeds the flight control system, and which, as needed, does the vehicle attitude correction or the thruster adjustments. And with the endpoint is we want to reach the phase end position with the necessary velocity, as you can see in the diagram on the right, uh, at an altitude and at a distance within tolerance. So after 11 minutes, it was left with only about 250 kilograms of fuel. And the control system brings the craft to the most important milestone. It deposits that craft at 32 kilometers from target, and the altitude is about 7 kilometers. So the mass of the whole vehicle now has been reduced from 1750 kilograms to about 900 kilograms. And because the gravity is so low, it weighs only about 150 kilograms force. So at this time, it might be useful to look at so in this particular diagram that you have, you can see how shallow a trajectory is. On the top, you can see the scale 2D trajectory, where the vertical scale is same as the horizontal scale, and you can see how shallow it is, and you don't see the curvature of moon. The the 10x vertical detailed geometry allows you to at least visualize where is the rough braking ending. So rough braking, all the four engines would end, and in the last 10 seconds of this phase, the vehicle's attitude, the control system will freeze, and the attitude will be maintained. And at this time, Anjali, can we see the second picture?
Sure, I would request Satyaji if you can please show the second picture also.
Oh yeah.
We can bring it up on the screen.
While he's getting the second picture, Mr. Arun, is it this communication that happens? Is it real time?
At the time of this descent down to the craft, there is communication for control purposes happening. Only diagnostic data is being transferred, and this diagnostic data is being transferred by Chandrayaan lander, both to the, I believe, the orbiting propulsion module as well as directly to Earth. And the Earth connection is through deep space communication satellites, which we have one at Hassan in South India. And this is also networked with other deep space networks of US. Um, so together, it's a cooperative program, and the information keeps coming back. But in terms of it doing the descent, it is on autopilot. Everything is decided by the computers on board based on the sensors that it is seeing, and they really designed it for great amount of failure that could happen, one or two or three, and that's how it happened.
So, Arunjit, the landing was picture perfect. It was just picture perfect. So, I want to ask you if I mean, was there any scope of error? Is it like it has to be picture perfect, or it's going to fail? Is it just zero or one, all or nothing, or there is a scope for some error?
There was a huge possibility of failures that were stacked up against uh, any engineering team, and they meticulously worked on it. And then they were aiming for not just perfect landing, but they were even planning for a degraded performance and what could be an alternate. So if it does not land at the exact point, it can still softly land there. That is what was planned here. So what I wanted to show you in this particular diagram is, as you can see, this is not to the scale on the vertical axis, also on the horizontal axis. But you can see the rough braking is ending at 7.4 kilometers. And that's where the horizontal velocity of the craft has been reduced to about 358 meters per second, but it is descending at the rate of 61 meters per second. So in the last 10 seconds of the rough braking phase, the vehicle attitude is locked, and that allows the camera to glance down, figure out exactly where you are on the moon surface, because uh, you know, these many kilometers down, 32 kilometers down, is where you're going to land. And at this time, which is a 10-second phase, you can see here attitude hold phase. This is the time when the camera is able to also see the landing location at about 18 degrees dipping angle. So it has got a fairly good view of where it is going to land. But most importantly, in this attitude hold position, the whole navigation system is calibrating itself to figure out, okay, I'm there. And this is 99% of the mission is kind of done. I'm at the right place, right velocity. And this is when you get the accurate fix. And if the navigation system or the thrusters have overperformed or performed under, if there is an error, then at this moment, the system knows what is my error, because that error will be corrected out in the next fine braking phase. So a huge amount of risk is really mitigated if you have a successful rough braking. So after that is done, then the craft transitions to a fine braking, and that is when the Chandrayaan is at about 6 kilometer nominal altitude. The velocity is like 330 meters per second, still going down at the rate of 60 meters per second. At this time, the craft now fires only two engines. So out of the four engines, it has decelerated good enough. Two engines are good enough to do the fine braking. Fine braking phase is where the fuel and the thrust is used uh, in a great amount for the given amount of deceleration that happens. That is less, but the amount of control and vertical um, acting against the gravity of moon is where the fuel is really spent. So now it fires just two diagonal engines, each with 81 kg. The thrust can be modulated, increased, decreased, as well as the direction of the thrust can be adjusted by the controller. And this time, gradually and very accurately, it decelerates the vehicle to a standstill in about 175 seconds, by which time it has traveled 28 kilometers and now directly overhead the landing spot. So this is where the landing spot is 1 kilometer below it. And once it reaches that, then the fine braking is ready to transition to a vertical descent phase. And by the end of the fine braking, all the navigational errors, all the flight control errors have been corrected. And that is what makes it picture perfect. And this is verified by when it is hovering, it looks down at the cameras, altimeters, and velocimeters and say, okay, I'm here, this is my current velocity. And then it starts descending down. And that is when the terminal descent phase starts. And when the terminal descent phase is starting, the vehicle orientation and the two thrusters, they reduce the attitude to reach the final point, which is really the decision threshold at about 150 meters. And that is when the craft again hovers, and for the last time takes the images to determine, is it safe to land below? Is the surface uneven, or some big rocks that could not be seen earlier could jeopardize it? And so the camera take the pictures, and then if there is a need that this is not safe, then there are pre-programmed set of alternative landing spots the system already has. So it can go out almost 150 meters and land in one of those other alternative uh, places. Now, this decision is all local, and this is all artificial intelligence, machine learned coding that is done. Uh, and this is where, in this particular flight, the Chandrayaan 3 did see a problem, and it the control system came to a rescue. So it automatically changed an alternate location, and then very gently aligned itself to the, and that is the time the craft is also oriented so that the solar panel is facing the sun, and the ramp through which the Pragyan will go down, it should see a flat surface. So it just orients in a way that the ramp is also not uneven, so that the four legs kind of land in a near plane surface. So that final vehicle orientation is done at that time, and then the vehicle descends down. And when the four legs make a contact with the surface, the engines are cut off. And that to me is picture perfect. Nothing could have gone better for a very, very successful landing. And that is the point, as Narayananji said, the nail biting morphs into euphoria of joy for all the Bharatvasis. And after some initial check, then they roll off the Pragyan. And this roll off is very carefully orchestrated by Vikram, because as it is rolling down, the Vikram is continuously measuring through laser distance finding the movement of the Pragyan to make sure it is lined up with the ramp and the speed at which it is going down is not slipping, for example. So again, nothing was left to sensor failure. Everything was instrumented, and the software code that was written was this time really, really excellent. So that is about the landing, and now uh, the Vikram and Pragyan, they will land. They were loaded with 5 experiments. Vikram had 3 experiments, and they finished all that business in 7 days. Um, and for the first time in the space history of this world, India has decided to release all the data that is collected to all the humanity. None of the data was privately hacked, unlike other spacefaring nations who only release some data and then keep much of their other data for themselves to continue to have that edge. India decided to really be more humane and favorable to all human beings. And so the Vikram lander had a Ramba LP. It measures plasma, and that will help decide, better understand the moon environment. It's essentially a high impedance uh, electrostatic probe. Then we had a Chandra safe thermo physical examination experiment, and this to me was startling. It measures the thermal properties on the lunar surface, and and it was very interesting that it found very high thermal insulation on the dust that is on the moon, and it also saw a very significant temperature gradient from the surface of the moon. As you dig down, the temperature changes very, very rapidly. And that to me is very exciting because that can make for human comfort, as in when you decide to get there. That area is very attractive. Also, Vikram had the instrument lunar seismic activity sensor. Unfortunately, on the second day itself, it measured a earthquake in moon, and it captured it pretty effectively. The Pragyan rover is currently about 100 meters out away, and Pragyan rover is essentially measuring the chemical composition on the surface through 2 independent uh, sensors. One is the laser-induced breakdown spectroscope, and that essentially um, blows, vaporizes the material on the surface, and then it does a spectroscopy that allows you to identify the material composition, what element and what proportion is on the surface. And this data is correlated with the second sensor, which is alpha particle X-ray spectrometer. And all this preliminary data has been already made available. And I, as a scientist, am very excited to see and confirm the information on material in the south pole of the moon. So
Thank you. Thank you so much, Arunji. I think this was such a great explanation. So I would request our viewers that because I understand that there was a lot of scientific terminology that was used and a lot of explanation that was given. But I think it'll be a great idea if our kids can watch that. There is so much to learn, and we have all these scientific geniuses out here. It's very difficult to get hold of them. Let me tell you that. So please, I know it may seem a little lengthy, the explanation, but it's worth it. And I would request you to have your kids really watch that. And thank you so much, Arunji. I mean, it's because of scientists like you that, as I'm going to use that phrase again, picture perfect. The picture perfect landing of Chandrayaan happened. So thank you. It was great. But I have my next question is actually for Shashank. I know he has been waiting for some time and he has something to show to us. So Shashank, you are an avid model builder, right? So
Right.
as yeah, so as an avid model builder, what parts of these missions seem most appealing to your home audience?
Right. I have two kids, and they love. I mean, they love building models, and undoubtedly, to me, the Vikram lander is the most appealing one. All the satellites and the Chandrayaan, for example, Chandrayaan 1, Chandrayaan 2, and what we have is the Mangalyaan. All of these to look more or less a bit similar, but yeah, let me show you. I do not know
Yes,
how.
please. Yes. Do you think you
Yeah,
can
if you
lift
can
it a little
see
higher?
me.
Yeah. Oh,
Yeah, this is the Vikram lander of Chandrayaan 2, okay, which is
nice.
very
Very
similar to Chandrayaan 3. And this is where the Pragyan rover came down. And this is a model of the Pragyan rover, if you can see it. If it get meshes with my shirt, then I apologize. Should have worn a different one.
not at all.
But this,
I think I can
yeah,
see it clearly.
right. So these two are more or less similar to what was built for Chandrayaan 2. Professor Satya can correct me if I'm wrong. The biggest difference was that in Chandrayaan 3, before Chandrayaan 3, ISRO made sure that Vikram did not miss a single leg day. So they put more weight on the leg. And then as a result, Vikram gained about 200 kilos as opposed to Chandrayaan 2. Um, Personally, I feel that, controlling a rover, whether you control it across the room or across, use light speed, takes a few minutes to get to moon. It's more or less similar. But as Professor Arun was explaining a bit earlier, the landing of the Vikram lander, I mean, that absolutely is mind-boggling to me. And if you remember, Dr. K. Sivan, the former ISRO director, had specifically mentioned that 15 minutes of terror, and there is nothing much we can do. You just watch. Can't do much at that point, because the algorithm has to take into consideration the data has to be gathered, then it has to analyze, then it has to run probability criteria, and then it has to make a decision. All within the split second, as Arunji mentioned earlier. And as someone who has written code my entire life, you know, I know Chandrayaan 2 used Python and C++ mainly for the algorithm. I'm assuming that Chandrayaan 3 will also use the same thing. I haven't looked at the code base yet, but I can only imagine the thrill the developers and especially the testers felt, when the Vikram did the picture perfect landing.
So
Thank
tell
you.
me, sorry, Anjali, I wanted to ask whether these are commercially available, Shashank, in the market for kids to buy.
These, yeah, this I actually got it from Amazon.
Okay.
I got it from
Okay.
Amazon.com, but you can get it. The same is available in Amazon India as well.
Okay. Thank you.
Yes,
Thank you. That's
yes,
a
my
good
Look,
point. Mm. Oh, you
Professor
have got it
Narayan
too.
also has it.
I have
Okay.
it. Yes.
Narayanji, do you mind showing it again? I think I just had a glimpse and I couldn't see it properly. If you could, for the
So
benefit
he
of
must
our
have,
audience.
he has to get
Disappeared behind the moon. Oh, here's
Oh,
my Chandrayaan
hold it
3.
closer to your
Chandrayaan 2
chest,
actually.
Narayanji.
Land.
hold it closer to yourself.
Hold it
Oh,
closer to yourself.
yes,
Yeah.
that's right. Yeah. Oh, very
And there you
nice.
go. And there is, I think, the GSLV that Professor Satya was talking about. Uh, and I think I have a whole bunch of other things here. And this is I've been building this. Well, I'm sorry, things tend to fall apart. I've been building these for a long time
Oh, you
for
broke something.
about construction, and it's a fantastic learning exercise. Usually these models are
Yeah.
also, well, not this tiny one, but the aircraft models that I've worked with are actually accurate enough. And once NASA told us, they asked, "Where did you get your models from? Your data are very good." And I thought they were going to drive me out. I said, "Oh, we're a poor university. We buy these at hobby shops." They said, "Which hobby shop?" Get it? We get it at the same place. So they, of course, they do some correction too. So this, and again, a fantastic learning tool. I was so impressed with this. I don't want to do any commercial advertising, but yes, you can get it on Amazon India.
So
Yeah.
I have a question, while we are talking about this space research and these models, uh, and of course, we have a bunch of professors here. My next question is for Professor Satya. Can you give some comments or advice on university role in Indian space research? Any, research training, basic education.
I think there are multiple ways by which ISRO is engaging with universities for what they want to get done. In fact, ISRO has what's called as ISRO, for example, but IIT Madras, they have something called an ISRO IITM Space Technology Cell. And similarly, they have with ISC a Space Technology Cell, IIT Kanpur, IIT Bombay. So they have for something called Space Technology Cells everywhere, pretty much all the major institutions in the first place. So they allocate budgets for each of these cells annually and solicit proposals from the faculty of these institutions that they will have to collaborate with a specific ISRO scientist or a group of scientists in a particular ISRO center. And they have representatives from all the centers at this joint policy committee that meets every now and then to look at all these proposals. And so there is a way by which the group that the faculty members are working with in ISRO will have to vouch for it, and they shape up the proposal, and then it comes up to the committee. The center representative there actually vouches for it, and then they pass it on, and then we get these projects done. So there is a very close buy-in from ISRO on the projects that faculty members do. This is with the major institutions, but they also have an open program called Respond, and Respond I think stands for sponsored research, but the mnemonic is actually kind of flipped around to make it sound nice. So the Respond program essentially allows for calling proposals from different institutions, and then that's actually a very vibrant program by itself that's open to all the universities. And obviously, ISRO, being so frugal, they will do projects only if it really is required by them, and they will make sure that they will take it to the actual application instead of just letting it sit there as a report. That's the second thing. The third thing that I'm particularly personally proud of is I personally have guided many ISRO scientists as for their PhDs. In fact, pretty much I have, I think, um, one PhD student who did the noise suppression from Sriharikota, another master student from there. There is a one PhD student from VSSC, one PhD student from LPSC, another PhD student from IPRC, the ISRO Propulsion Research Center, then Liquid Propulsion Systems Center, and VSSC is Vikram Sarabhai Space Center. So pretty much all the propulsion centers. I have one student each at least, I'm just a representative of so many others, who have ISRO scientists as their, PhD students. For example, the Chandrayaan 3 project director, Veeramuthu Vail, actually did his PhD with one of our colleagues at IIT Madras while he was while he has been at ISRO. So that's a huge, intense relationship that's actually getting built up between the faculty and the scientist who is actually the PhD student. Both of them learn a lot from this and then enrich themselves and the ISRO program.
That's very encouraging to know. So, Nivedita ji, do you have any comments on India's aspirations?
I think, more than the comments, I have a lot of questions, and it's for me, a person, and I look at myself as a layperson. I think it's to understand the thousands of scientists who have worked behind it back end and the kind of work that has been done. I think it's mind boggling. And I think that itself gives us so much pride. But tell me, I think either Arunji or Professor Satya, why the South Pole? Is it really that important? And is it that we are expecting to find some precious metals there and maybe a lot of gold or platinum, and maybe that will come back to the earth? Why did India choose the South Pole? Is there more significance to it than just the fact that nobody had ever gone there before?
I can take a call on that.
Yes,
And
yes.
so, South Pole is very important as a staging area for extra or intraplanetary travel. So, the the rocket fuel and the size that can determine how much payload can go how far out uh, will force you to build extremely big rockets. What what lunar south pole allows you to do is you could possibly use that as a staging or transit area. So you could transit your rockets from here to the moon and then reconfigure your rocket to go further. A very interesting aspect of being able to do that is the southern pole of the moon has got a lot many more craters. And because of the very oblique solar insolation, these craters have got what is known as cold traps. That is where the sun never shines no matter what. And these cold traps are so cold that when meteors or other things hit that have got any water that disperses there and stays cold can never be evaporated back. So over the past, few billion years, the cold trap is storing uh, material, particularly near water-based, either water or frozen water or hydrate that can from which you can easily extract water. Now that is important because water is both uh, a material that is needed for human survival. Water is also a potential rocket fuel. You could trap the heat coming from sun or have a nuclear reactor, and from the electricity there, you can convert the water into hydrogen and oxygen, which is really a rocket fuel. So if you use uh, moon as a transit point, you want a place where you can set up a factory or human beings can go there so you can extract resources and do travel out to other planets with much smaller and cheaper rockets compared to launching those rockets from Earth. So that is the reason why South Pole is very important. And in terms of material that can be extracted, I think the only material that can be extracted for now is water. Do we care for gold or platinum lying there? Perhaps not, because by the time the energy is spent and the cost spent, to go fetch the material from there to Earth would be much more expensive than extracting the same material from, say, seawater. So I'm yet to be convinced by the fiscal viability of extracting material from there. What the only thing that makes sense is as a staging post to go somewhere.
Yeah.
And the
That was
reason
sorry,
and the
sorry.
reason the South Pole is interesting is the long term line of sight. It is visible from Earth, so you can directly communicate with it. So future human missions, that's very interesting. You have got water, uh, and the angle at which the solar radiation is coming really makes it very convenient for you to stick out solar panels, get the energy, maybe super hot, but down below it is pretty cold. So it's very easy to build a refuge for human beings or for your factory. Uh, then the asteroids that constantly hit planets, the asteroids hit at a very oblique angle, so it is much more protected by asteroid hit compared to anywhere else. So the poles are much more suitable. Now the poles do have very extreme temperature range. Uh, During sun time, it could be going to plus 120 degrees centigrade, and it could go as low as minus 200 degrees centigrade. So environmental control would be a little challenging, but given that the surface dust is very excellent insulator, it does allow you to, dig up a habitat for yourself.
So you're saying that in the next few years, few decades, we can think of having a civilization or maybe a tour to the moon.
Yes, it is possible moon, but maybe more likely a tour to Mars, and that is transiting through moon.
That's interesting.
Yeah, good one. But I have a question for Narayananji. You have a curious designation, chair of the Taksha Alliance for a Space Economy. So what is that, Narayanji? Also for our viewers, Professor Narayanan Komrat was an invited expert witness in 2004 before the US Presidential Commission on the Future of the US Space Program, also known as the Moon Mars Commission, and he spoke on the coming space based economy.
So, thank you. Let me just get on my soapbox for a little while there. Back in the 1990s, NASA and other US organizations actually got together and created something called the NASA Institute of Advanced Concepts, NIAC. Now, as Professor Satya said, there is a very tight linkage between NASA program managers and research and budgets and universities. And a lot of times, university research is driven by what NASA wants today or tomorrow. That's forced by the budget. So this actually said we want an arm's length or farther relationship from NASA, but we want NASA to look over it, but not kill any projects. NASA had, they could kill a project saying, "Oh, that's been done before," but nothing else. So they said, "Don't let your preoccupation with reality constrain your imagination. Tell us what could happen in the next 30 years. It has to be at least 10 years out. Otherwise, NASA managers will use it for tomorrow's mission to relieve their budget pressures. It can't be more than 30 years out because that's too far. So tell us about things that can happen." So what I'm going to tell you is the things that came out of that actually. A space based economy is defined as an economy where the suppliers, the raw materials, the vendors, the customers, the delivery service are all located beyond Earth. So, what is Earth? Well, Earth is a very nicely kept, expensive tourist destination. Children grow up and say, "Oh, we want to go on a vacation to Earth sometime. I heard it's so nice over there." They have actually storms, which we never have because weather is controlled where you are, and things like that. Why? What's out there? Well, the resources available in just the near solar system, which includes the asteroid belt, as Arunji just mentioned, that makes all our earth resources, all the things, oil, gold, whatever it is that we fight over, these look so minute, negligible in comparison. There's so much out there. Just how are you going to get it? In time, economic development will come. Sabke saath, sabka vikas. It cannot and should not be done by somebody going out there and saying, I'm going to bring a platinum asteroid and crash it into the Pacific Ocean and corner the market. Those are all very silly ideas. So, on that point, I do want to state my very, very strong disagreement with the notion of mining the south pole of the moon for water or water ice or whatever it is. I don't think, first of all, there's not like oceans or lakes out there. There's tiny amounts inside craters, which if you mine the crater and dig out 100 tons of stuff, you might get a few grams. I think it should be absolutely prohibited for anybody to do this just to use it as rocket fuel and make more money. This is the worst use you can imagine for it. It should be totally prohibited by all nations. The ice that is there has been there for billions of years, and it can tell you the history going back at least to the beginning of the solar system. It is a fabulous uh, resource of humanity. And so are many of the other things there. I really don't know what else is out there. I think they found sulfur, which brings some very interesting points. But anyway, so why should I be in the space-based economy and prohibit economic development? Because there's other ways to do it. There's something very, very, very abundant on the moon. That is oxygen. It's not in the atmosphere. They don't have an atmosphere over there, but it's in the soil. It's silicon dioxide, manganese dioxide, whatever it is, oxides. There's so much. So why don't we mine oxygen on Earth? Because you can't get a good price for getting oxygen out of silicon, out of sand. It's out in the atmosphere. It's free. But on the moon, you can simply use solar heat and the nice vacuum atmosphere there. There's no atmosphere, there's a vacuum processing center. And you can make as much oxygen as you want. If from science classes, you know that water is 16 parts by mass of oxygen and 2 parts of hydrogen. Okay? The hydrogen is what is missing on the moon, not easy to get to. So you take the hydrogen from Earth, you mine the oxygen. You don't have to mine the South Pole for that. You can get it all over. Anywhere you dig up, you can get oxygen out of it. You store the oxygen and you have your rocket economy. As Arun said, you can go to Mars or wherever it is. Fantastic. Staging point. I totally agree. All the other things I totally agree. But first thing that is needed is very tight global laws which already exist, prohibiting, and don't relieve that prohibition against using up stuff that has been there for billions of years and is really the property of all humankind for the future. Now, having said that, there is a way to progress in the space-based economy with the moon. And digging up the moon for oxygen. Let me tell you a very brief example, if I may take a moment. This is very rudimentary economics. Now, suppose you want to get iron on the moon. There's iron oxide. Okay. So how do you turn iron oxide into iron? You have to take hydrogen there, and you have to take a tiny bit of carbon or sulfur, whatever it is, and use a lot of heat, and you can get iron and water. Very costly. Hydrogen costs just as much as anything else to ship from here to the moon, which last I saw the calculation from American sources was on the order of $20,000 per kilogram. It doesn't matter whether you're taking mud or hydrogen or gold, it costs $20,000 a kilogram to get it to the moon. Not cheap. So how are you going to make money of it? Well, it also costs that much to take water to the moon. So the byproduct of this iron oxide reduction is water. If you have a market for water, you make more money out of it. This is the concept of the space-based economy. The more industries, more ideas get together and collaborate instead of trying to kill each other, the better that economy can work. And so, to me, the ultimate goal is not some huge scientific nuclear plant or whatever it is on the moon. To me, the real test of whether we have arrived with the space-based economy, it's a pizza delivery service in orbit. Think about it. Okay, we once asked a bunch of kindergarten children, what would you do if you had a job in space? And it was an undergraduate who made the presentation on, showed a lot of things about what goes on in the space station. They were really fascinated because your hair stretches out long. There's the lady astronauts who had their hair just stretching out long in microgravity, and they saw that you could pass food by just throwing it very gently. So there were a lot of people who wanted to go into food service. Hey, there's a place where I can toss the food to the customers and not get into trouble. A lot of people wanted to become hairdressers. Many people wanted to become basketball arena magnates because you can shoot such three-pointers in 1/6 gravity. So fantastic. Not a single one. These are obviously parents who are involved in these homework assignments, I can tell you. I have some fantastic pictures somewhere on my computer, but I couldn't find it. Not a single one wanted to become an aerospace engineer, certainly not a professor. A bit disappointing, but that is the economy. Economy is not all nerds or geeks or whatever you call it. Economy is people doing a whole bunch of different things. And that's what the space-based economy is. Thank you.
I think this was such an
Yeah.
informative session, but sorry, Nivedita, did you have a question?
Yeah, I wanted to. Yes, I wanted to come to Shashank and ask him because he's part of the fintech ambience uh, in India and maybe also globally. Um After listening to what the scientists have to say, do you think there is a role that the medium and small scale manufacturers in India can play in India's space program? Because you know it is there could be various models, or should we go
Right.
to the model like the US United Space Alliance, where NASA merely awards contracts to a large conglomerate, or is ISRO would go the other way and take up the MSMEs? What do you think of that, Shashank?
Right. I'll keep it short, Nivedita, because I know we are a bit over time. And so, yeah, let me answer the second question first, because the thing about the NASA model, I would rather have ISRO heard a vast array of small companies than unlike the NASA model where they give out the projects and then expect the companies to do. Part of the reason is that, according to the Government Accountability Office of 2021 report, specifically mentioned that the NASA project's overrun was about tune of $9 billion just for the year 2021. I think ISRO 9 billion would give ISRO a few years of runway, given the way that we are sending satellites to space for budgets far less than what it takes a Hollywood to make a movie. So for that particular reason, I prefer ISRO handling it and then giving out components for different SMEs to work. Prior to 2014 or even prior to 2020, I would say, because that's when the laws were changed. Prior to that, the only, or Professor Satya could correct me, but the only MSME that I could think of which worked with ISRO was um, what's that? Anant Technologies, which was started by somebody from ISRO, Sri Paolo Risubarao, who left ISRO and then created the Anant Technologies. They used to help ISRO on and off in every single thing that they did. But right now, I think. But I think right now, with what ISRO and what Modi government has done, is they created the SEED, or the Space Enterprise Encouragement and Development Fund, which specifically gives money to MSMEs to start working. ISRO gives them the technologies, ISRO helps them build everything, and then they start producing things. And um, for the Chandrayaan mission, there was a small startup called Bhubaneswar Tool room, which produced about, if I read, about 54,000 components. So the Indian space ecosystem is just beginning to sprout, and I would assume that in the next 10, 15 years, we are going to see a full thriving ecosystem. And
Thank
it's going to be mostly by MSMEs, and
that's
because
it.
big companies have other issues to take care.
Yeah,
Sorry.
that's it. That'll be just what the Indian economy needs. Thank you. Yes, Anjali, over to you.
Well, actually, there is so much of information that I got today. And I must confess that it's not like I understood every single scientific term, but the way Professor Arun explained, the way Professor Satya explained, the way Narayananji explained, Shashank and you, Nivedita ji, I think I think even as a layman, it was not very difficult for me to grasp. When Professor Arun talked about the trajectory and the different phases of the Vikram lander, I think it was just remarkable. And we are very fortunate that we had this opportunity to have somebody like Professor Satya, Professor Arun, to explain this to us one on one. I'm really very thankful, and I have Bharat TV's CEO Manan Rawal. I'm going to add him to the studio here. Um, he would like to thank you. Can you hear us, Mananji?
Yeah, I can hear you properly. Somehow I'm using somebody else's computer, so I'm really sorry that I cannot switch on the camera over here. But I'm really obliged and thank you all the senior scientists who has come and explained in detail what exactly and how this happened. And we are still waiting for our sun mission to be there on. And if we can go live with that, I will be much grateful with that. Only can you make plan for that too?
Absolutely. I think once once we are done with this program, I will. I'm going to run behind Professor
Yeah,
Satya.
when that is going on, we can go live with those stuff, right? They are. I was listening from after 10 minutes. I was live there, and it's fabulous. Heads off to you guys. Thank you so much for joining us, and really obliged.
And
So
thank you, Mananji. Thank you very much. I
Good day.
think this is
Thank you, ma'am.
wonderful work. And I have to congratulate you. You have taken away the Bharat name in advance.
It was in 2018, madam.
Okay. Very far seeing. Yeah.
कण कण में हिंदू, रग रग में हिंदू, हिंदू मेरा परिचय है.
Mhm.
This
so
is there.
So, dear viewers, the journey has indeed just begun for this great land, Bharat. Rooted in a glorious past of an ancient advanced Vedic civilization, for India, Chandrayaan is just the beginning of its tryst with this vast, enormous, undiscovered space called the Milky Way. It was an honor to interview a panel consisting of scientists who were pioneers and instrumental in arranging the meeting of our Chandrayaan with its Chandra. When the breathtaking landing took place on August 23rd, I'm sure, just like me, you too have enjoyed those moments of history in the making. So let us all wish them all the very best for all the upcoming adventures with space. Thank you and namaste.
Namaste.